Hello everyone. I'm Sobhan. I'm a PhD student under Prof. Ranjan Singh in Department of Physics and jointly in Department of Physics and Center of Disruptive Photonic Technology at Nanyang Technological Universities. I'd like to thank the organizer for allowing me to speak on behalf of my supervisor who could not be here due to some personal reasons. I would like to start the talk by showing you this beautiful terahertz pulse and to motivate ourselves, everyone here, what a beautiful field that we are currently exploring. So let's start. Okay, so the technology, we know the technology have come to a fabrication limit where it is difficult to fit more number of transistor into a very small unit area, right? So we need to overcome this fabrication limit. We need to increase the working frequency, but this working frequency has been stagnant for the past couple of years at 8 gigahertz, which is roughly around 20 picosecond, because this frequency is directly related to the working power, right? So the power consumption. So as we increase the frequency, we have to increase the power consumption. So we need energy efficient devices for which we need to decrease this time scale, and for which the ultrafast spintronics, which is basically our work of our research field, is very crucial. And I would like to take the opportunity to repeat few of the slides that we are still discussing for the past 2 days now. So for this, what we have is the ultrafast femtomagnetism, where in a seminal work it was shown that when we photoexcite a ferromagnet layer, the electrons, the spins basically, try to move away from the excitation region, and while moving it away, because of its movement, there is a sudden change in the magnetization, which is in the ultrafast time scale. And further extending this work, actually, which we call it as ultrafast demagnetization, extending this work was Prof. Marco's work, where he showed that once we have a layer adjacent to that ferromagnetic layer and we photoexcite that ferromagnetic layer, what happens is the spins that is moving out of away from the photoexcitation region super diffuse into the adjacent layer, which is an aluminum layer. And then Prof. Tobias did that groundbreaking work where he replaced this aluminum layer with a high spin orbit coupling heavy metal. So when the spins are super diffuse into the adjacent heavy metal layer with high spin orbit coupling, the spin is converted into the charge current due to inverse spin Hall effect following this equation. And then this charge current, because it's accelerated, it generates terahertz pulse. And because these are very thin layers, we don't see the band gap. We see a gapless terahertz emission from the entire 0 to 30 terahertz band, right? So when we dwelled into the system, in around 2018, and it was at a very nascent stage. So we started exploring the peak field of the emitted terahertz. And in our preliminary measurement, so this is the schematic of our measurement setup, where we have the emitter here. This is the magnet, and we pump the laser to the emitter, and with the delay stage we detect the terahertz through electro-optic sampling. So when we were during our preliminary measurement, what we are doing, we were checking the emitted peak terahertz pulse with the sweeping of the magnetic field, and we saw a remarkable similarity between the terahertz pulse amplitude with the magnetic field with the popular MH hysteresis curve. And we thought this might be a fluke. So what we did is we changed the magnetic field direction, which was initially perpendicular to the easy axis of the sample, and we changed it to the parallel to the easy axis, and we saw the similarity again in that case also. So we understand that yes, there is an magnetometry process that is happening here, but intuitively what we expect is the terahertz electric field is actually proportional to the time derivative of charge current, and the charge current is directly proportional to the spin current, which is directly proportional to the magnetization, right? So intuitively what we can think is the terahertz electric field is directly proportional to the time derivative of magnetic field, which is not happening here, right? So then we we didn't have the basic understanding of what's happening here. So we took the help of Prof. Marco, who helped us model a very theoretical he helped us develop a theoretical model, and through the theoretical model we realized that though the terahertz electric field is proportional to the time derivative of charge current, the peak terahertz field is directly proportional to the peak charge current. That means the peak terahertz field is directly proportional to the magnetization, and hence this direct correlation between the VSM data from for MH hysteresis and the terahertz hysteresis data with the magnetic field matches. So this is a Spintronics bilayer that we started with, an IFEPT, and we call it as Terahertz Spintronics magnetometer, and we checked with typical trilayer also, which is WCOFEBPT, and some monolayer COFE also. And with monolayer, though we saw the matching of the VSM and TSM, but we saw an interesting phase change, and we saw it only for COFEB, not for NIFE. For NIFE, we did not see the phase flipping, only for COFEB we saw the phase flipping. Now if the terahertz is emitted because of the ultrafast demagnetization, then there should not be any phase flip, right? So once we saw the phase flip, we understand that there might be some spin transport or electron transport depending on our understanding. There is some transport phenomena happening, but it's a very complicated process, and we are still working on that. Now that we have the understanding of the terahertz peak field with the magnetization, we came back to the original question, which is how to manipulate the spin in ultrafast time scale. Although the ultrafast demagnetization is basically a intuition that we are manipulating spin in ultrafast time scale, still for device application what we need is we need to switch between individual spin state, and for that we need to jump this magnetic energy, and to jump this magnetic energy we need to decrease this magnetic energy, and we realized that with increasing laser intensity or laser fluence we could decrease this magnetic energy, and that we saw again with our terahertz spintronics emitter, and we saw that when we increase the fluence, the coercivity actually starts decreasing. At a larger fluence, the coercivity was very less, and then as we increase the laser fluence, we saw that till around 0.6 millijoule per centimeter square, the coercivity was flat and very high. Then it suddenly decreases in this region, and then again it became flat at from 0.9 to 1 millijoule to 1.5, and it became flat again. But the terahertz amplitude is increasing as we are expected, because we are exciting more spin current, right? So this is a color plot of showing that yes, the peak field is actually the coercivity is actually decreasing as we are increasing the fluence, right? So if we are staying in this magnetic field, let's say, then if we increase the fluence, we could easily flip the phase from the color plot, right? And we did that measurement, and we saw that yes, as we increase the fluence till a certain fluence, which is 1 millijoule per centimeter square, the phase was constant, and then it flipped. But when we remove the fluence, it did not flip it back. So it's a most desirable memory effect that we could create. So basically, in summary, what we saw at around this magnetic field, 0.5 oester, when we have higher fluence, a lower fluence, we did not see the phase flipping. But once we increase the fluence more than 1 millijoule per centimeter square, the phase is flipping. So it's basically an ultrafast photothermal phase flipping of phase manipulation of terahertz emission. Though we flip the phase using pump fluence, for device application we need to manipulate the spin current using electrical stimuli also. So for that we need a ferromagnet which is sensitive to electric field, that is a ferromagnet and a ferroelectric, which is a multiferroic, right? But the limitation is we don't have much a very high number of multiferroic at room temperature. So we need to devise a synthetic multiferroic material, which is basically a ferroelectric substrate, and we couple it with a ferromagnetic material. The ferroelectric substrate that we use is PMNPT, and we deposit ferromagnetic material over that ferroelectric substrate, and we generate a synthetic multiferroic material. But the problem is when we deposit a ferromagnetic material over a ferroelectric material, there will be charge coupling across the interface. So when if the charge coupling is there, then the strain will not be reversed when we remove the ferroelectric. So to minimize this charge coupling, we introduce a heavy metal layer in between. Heavy metal layer does two things, right? One, it will minimize the direct charge coupling between the interface, and second, it will also provide the spin to charge conversion for Terahertz emission. We use PM, as I said, we use PMNPT for as a ferroelectric material, and in PMNPT we see that if we apply an electric field, the electric dipoles are out of plane to each other, so there will be maximum strain. And when we apply a less electric field, the electric dipole will be in plane, so the strain will be minimum. At -8, the electric dipole will be again out of plane, so the strain will be maximum. And when we deposit a ferromagnetic layer on top of it, the strain will transfer to that ferromagnetic layer, and there will be strain induced magnetization switching in the ferromagnetic layer, right? So when we did the terahertz emission, as I said, the strain will be transferred to the ferromagnetic layer, and at maximum strain and minimum strain, the magnetization switching will be happening. And we saw a very when we record the terahertz amplitude with electric field, we saw a very clear butterfly, well-known butterfly loop. And with the terahertz emission, we saw a 270% modulation in amplitude when the maximum strain is applied, and when the minimum strain is applied, we saw a modulation of 270% in amplitude. Another interesting thing that we saw, at maximum strain and at minimum strain, the retentivity magnetization is decreased when we apply the minimum strain. And using this result, we also wanted to check if we can flip the phase also using electrically. So what we do, we stay at a optimized magnetic field, which is we call as reset magnetic field, and when we increase the electric field, we could clearly go from positive phase, from B is a positive phase, to C, which is negative phase, and D negative phase. We could clearly go from B to C to D. As we increase the electric field, we could flip the phase also. So basically we could flip the phase, and we could manipulate the amplitude through electrical control, strain mediated electrical control in a terahertz emitter using a ferroelectric substrate. Now that we have manipulated amplitude of the terahertz emission, which is spin current, and the phase of the terahertz emission, to get a complete control of the terahertz emission, what we need to do, we need to control the chirality of the emitted terahertz also. So for that, we had to know the role of interfacial spin relaxation. So we expect that at the interface of ferromagnet heavy metal also, there will be some spin relaxation and spin to charge conversion, and that will also help us emit the terahertz. So we used a synthetic antiferromagnetic material. As we know, synthetic antiferromagnetic material is a kind of material where if we apply high electric field, high magnetic field, the magnetization vector will be parallel in, okay, the synthetic antiferromagnetic material is basically a heavy metal layer sandwiched between two ferromagnetic layers. So once we apply very high magnetic field, the magnetization vector will be parallel to each other in individual ferromagnetic layer. Once we decrease the magnetic field, the magnetization vector in one will be anti-parallel to other. So we will have a antiferromagnetic structure here, and in this case we have a entirely ferromagnetic structure. So in this ferromagnetic configuration, the magnetization will be supporting each other, whereas the emitted terahertz will be opposing each other, because the spin current will be traveling in this direction and in opposite direction. So the emitted terahertz will be opposing each other, where in this case the emitted terahertz will be supporting each other, but the magnetization will be opposing each other. So we again did the Terahertz Spintronics magnetometer, and we saw that yes, since the magnetization is opposing in this case, supporting in this case, but the terahertz is opposing, there is a complementary behavior. And similarly, when the magnetization is opposing each other and the terahertz is supporting each other, we saw the complementary behavior. So using this complementary behavior in TSM and VSM, we realized that the spin pumping from individual magnetic material, from ferromagnet to heavy metal layer, will be identical. So we need to create a phase difference between this these two spin movement from individual magnetic material to create the chiral terahertz emission. So we need to break this symmetry. So what we did, okay, so let's say this is region 1 where we have a magnetization supporting each other. This is region 4 where the magnetization is opposing each other. So we are decreasing the magnetic field from region 1 to region 4. So there will be an in between magnetic field where the magnetization will be perpendicular to each other. So once these are perpendicular to each other, these are, let's say, transverse spin. So transverse spin will be relaxing at a different rate than the collinear spin from this layer, and transverse spin will be relaxing faster, the collinear spin will be relaxing slower, because the transverse spin will be depending on the exchange length, whereas the collinear spin will be depending on the spin diffusion length, right. So once we create a asymmetry between the relaxation time of the transverse spin and the collinear spin, then we create a time difference between the terahertz emission in x and y polarized, right. And once we create the time difference, we create a phase difference, and hence we create a chirality in the emission. So we did that experiment. So we separate out the x polarized terahertz and y polarized terahertz using two wire grid polarizer, and we saw that yes, at around 0.7 kilohester we saw a elliptically emitted terahertz, whereas at 1.5 kilohester and also at 0.1 kilohester we saw the linear terahertz emission. We did some theoretical, we did some mathematical calculation, and we actually could separate out, as I said, the Ex and Ey and fitted it properly. So we saw that at 1 kilohester, as I said, there is a vertically linear polarized light. At 0.7 this is a more elliptical polarized light. At 0.5 this is again more elliptical, and at 0.2 it's again linearly polarized terahertz light. And note that in Ex Ey there is a delay when it is towards the circular polarization, there is a delay in the Ex and Ey polarization. For further proof, what we did is we calculated the phase difference between the Ex and Ey polarized terahertz emission by sweeping the magnetic field, and we saw that at 0.73 kilohester there is a 90-degree phase difference between the Ex and Ey, and this was over a broad band of 2 terahertz. And again, when we increase the magnetic field, the Ey is started, terahertz emission of Ey is started delaying, whereas Ex is constant. So there is a time difference there. So time difference creating chirality in the emitted terahertz. So we fine-tuned we measured the 3D chirality, and we fine-tuned the magnetic field, and at 0.74 we saw the clearly circularly polarized light, and the dumbbell shaped is basically linear polarized, proof of linear polarization. So at 0.18 to 1.2 we saw the linear polarization. So we could clearly go from linear polarization to circularly polarized light. We again fine-tuned the magnetic field again from 0.7 to 0.77. At 0.74 we saw a more circularly polarized, and with changing the fluence, we kind of tried to change the magnetic energy in the system also, and then at a magnetic field of 0.77 kilohester and 1.05 millijoule per centimeter square fluence, we could see a clear circular right circular polarization of 98% chirality, which means the elliptical angle was around 44.5 degree, and at 0.18 kilohester the elliptical angle was around 5 degree. So from vertically polarized light we go to the right circularly polarized light, and this is active tuning of the polarization of the emitted terahertz without any microstructuring. So this is just a 3-layer thin film structure. So we don't have any microstructure, and this chiral terahertz emission can be used as a probe to see the spin texture in the synthetic antiferromagnetic system that we have, right? In conclusion, what we have done is we have done the ultrafast Terahertz magnetometry, which we call as Terahertz Spintronics emitter. We probe the phase of we manipulate the phase of the terahertz emitted terahertz through ultrafast photothermal effect. We manipulate the phase and the amplitude of emitted terahertz through electrically induced strain transfer, and we manipulated the chirality of the emitted terahertz through magnetic field and the fluence. In acknowledgement, I would like to, so most of the works that we have done is done by Piyush Agrawal, who is we defended his PhD thesis last January. We like to thank all our collaborators. Special thank to Prof. Marco, who gave us theoretical simulation help, and his student. And we also thank our sample provider. This is our group picture. So, thank you.